In this video series, we are talking about comparing groups on a quantitative response variable. So that is, the explanatory variable is a categorical variable. It is a grouping variable in which we can have k number of categories, where k could really be anything, 2, 3, 4. But right now I want to take you back to your first statistics course when you compared groups. You most likely compared two groups. How did you do that two-group analysis? The effect that you were primarily interested in was the difference in means. So the setup was something like this. You had a population of interest. Perhaps that was a control group. And you had another population of interest, and that was a treatment group. Now, in reality, the population of interest in the treatment group is just a hypothetical potential population. That is, whether you select a sample from the treatment group where everyone in the population has been given the treatment, not very likely, right? Or whether you select a sample from the control group and give those members in the sample a treatment, that's the same as having a sample that represents a population of individuals who receive the treatment, even though it's just a potential population. So often what is done is we will take a sample from the control group, that is, a sample of individuals who have not had the treatment. We will randomly assign, and we will randomly assign so that half of our participants receive a control and half of our participants receive a treatment. And the control sample is going to be observations from the control population, and the treatment sample is going to consist of observations from the treatment population, although that treatment population only exists as a potential. But it is exactly the same as if we gave everyone in the population a treatment and then randomly drew to get our treatment sample. So it's a lot more efficient to take a sample of individuals and give them the treatment than it is to give the treatment to the whole population and then take a sample. So our primary interest is in the mean of these two conditions and how those means differ. We might think that we want to see the difference between treatment and control. I'm assuming here that high numbers are a good thing, and therefore if I subtract in this direction, I'm looking to see if I have a positive number. What in essence we can look at is we can look at the means for the sample in the control and the sample in the treatment. And so we have the mean of the treatment minus the mean of control for the sample, and we're using that to estimate what it might be in the population if we looked at the population mean of the treatment minus the mean of the control. So that's what I mean when I say in two-group analysis, the effect that was of interest is the difference between the means. As you know, the primary graphical display is side-by-side box plots, and we've looked at those in this video series, albeit for three groups, but it's the same sort of thing if we were doing it for two groups. Now, what we did not look at in this video series is a confidence interval. We haven't talked about how could we construct a confidence interval if we actually have three conditions. When we have two groups, we know that the most informative inferential statistic is a confidence interval for the difference in means. So we could construct some confidence interval in which we have a lower bound, and then that will help bound our interval about mu treatment minus mu control, and then we have an upper bound. And so, for example, if we ended up with a confidence interval that looks something like this, this would tell us that the mean of the treatment minus mean of control is between 4 and 11. In essence, what that says is the effectiveness of the treatment is to increase the average from between 4 and 11 points, whatever those points happen to be, whatever the units of measurement we have that we're using. Those units of measurement could be something like points on a test. The units of measurement could be on a scale. The units of measurement could be readings and blood pressure. So whatever it is that our units of measurement are on, this 4 to 11 provides the bounds for the effect size for our treatment, how much we change the mean when we switch from the control to the treatment condition. But what do we do when we have more than 2 groups? And that's the situation that we've been dealing with in this video series. The researcher must decide where to focus the lens. There are 2 possibilities. The researcher could focus the lens on a broad omnibus question of group differences. Now, you may not have seen that term omnibus before. Omnibus simply means that you are looking at all groups at the same time to see if there are any differences. In this context, the omnibus method is to look to see if there's any differences in any of the K group means. In general, omnibus simply means that you look at all the data at once. Whereas what we could do instead is we could have multiple questions about specific differences. We might want to know if group 1 differs from group 2, or group 1 differs from group 3, and so forth. So an omnibus null hypothesis, for example, would be that the means of 3 different groups are all equal. The specific hypothesis, if we're looking at individual group means, is we want to know if 1 is equal to 2. That would be the null. Well, that would be our first null, because we could also have a null hypothesis in which we look to see if 1 is the same as 3, and another one in which we look to see if 2 is the same as 3. So these would be specific comparisons that we could make, as opposed to this first null hypothesis, which is an omnibus hypothesis, looking at all groups at once. There is an advantage to an omnibus hypothesis, namely that you get more power with an omnibus hypothesis, that is, a greater chance of rejecting a null hypothesis when you look at all values at once than when you select certain values. Now, you may ask, why is that? Why would I have more power for an omnibus hypothesis? Think about the fact, first of all, that you are using participants from the entire study rather than participants from just some elements of the study. Think about what you would do in comparison if you were going to look at specific questions of interest. You may look, for instance, when you have 3 groups, you may look at the participants only from groups 1 and 2. And there's a general rule that there is more power, all else being constant, when you add the number of participants. Now, there are other reasons that I'll get into in a few moments about why there's more power with the omnibus hypothesis, but that's a good starting point. What's the advantage of specific questions of interest? I would contend the advantage is usually those answer the questions we're interested in. We're not just interested to see if one group is different than all the other groups, or whether you have any difference at all among all the different conditions. In the example that we have been using where we've been looking at worldviews, we're probably not just wanting to say, there are differences in the perception of airline risk for the different worldviews. We'd like to know whether one type of worldview leads to more perception of risk than a specific other type of worldview. And so when you look at multiple questions of specific differences, the key here is it's specific, you're indeed looking at specific questions that you're probably interested in. Now, talking about effect size here, what do we use as our effect size measure? Well, when we looked at the omnibus hypothesis, all we looked at is how much of the variation that we could account for with our model. That is, we looked at the R squared. But if you look at specific differences, what you can look at are the multiple differences in means. So you can look at the mean of group 1 minus the mean of group 2. That would be the parameter of interest. Of course, we would estimate that parameter by looking at the sample mean of group 1 minus the sample mean of group 2. And you would have those for all possible pairings of groups. So you have an effect size that is given in the actual units of study rather than looking at the amount of variation that's accounted for in your model when you look at all the groups at once. But there's a downside. The downside is there's a potential for an increased number of errors. If you think back to my example, in which we have all these different possible hypotheses, well, here for these specific comparisons down here, we have 3 different hypotheses. And so anytime you test a hypothesis, there's a possibility of making either a type 1 or a type 2 error. And that, in fact, would occur 3 possible times for each hypothesis. Whereas when we looked at the omnibus hypothesis, you can control the type 1 error just for that one hypothesis, and you don't have to worry about the fact that errors can compound. So we're going to have to consider as we move along, how do we deal with that? Because imagine if I were to deal now, instead of 3 groups, imagine if I were to deal with 4 groups. When I deal with 4 groups, there are actually 6 different hypotheses that I could make if I looked at the different pairs of means or the different pairings of the groups. If I have 5 groups, now there's 10 possible hypotheses. And so you can see how the errors can compound over time. So what we do to handle that is what is called multiple comparisons of means procedures. Multiple comparison methods provide error control not just for a hypothesis, but for a family of comparisons. So in the past, when we built confidence intervals, all we had to do is set a type 1 error rate, such as 5%, and we would build 95% confidence intervals for the one question of interest. But now when we have 3 questions of interest, what we would like to do is say, is there a way that I can be 95% confident in the entire set of confidence intervals that I construct? So related to these 3 hypotheses we looked at, if we indeed had 3 confidence intervals, and for each of these confidence intervals we had lower bounds, and for each of these confidence intervals we had upper bounds, this whole set would be considered a family of comparisons, and we could set 95% confidence, not for each interval, but 95% confidence in the entire family, meaning that when we look at all of our confidence intervals, we're 95% certain or confident that we have actually captured the true differences in means for all three of these differences in means. So that's what multiple comparisons of means is all about, and the multiple comparison methods that we use, they provide error control not just for a single confidence interval, but for the entire family of comparisons. Now, there are two main types of ways we can go about making comparisons. One of those is post hoc. And what post hoc means is that we go ahead and do the omnibus test first. That is, we look to see if there are any differences among any of the means first. And if we end up not being able to reject an omnibus hypothesis, we are done. We stop. On the other hand, if we find out that there are differences in the means, then we continue on and say, okay, I wonder where those differences are. So back here in this situation here, where this first one was the omnibus, we go ahead and do that test. And if we're able to reject that null hypothesis, then we can look at three different specific hypotheses, or better yet, and what we want to do is we can now construct those confidence intervals. If we have no reason to believe that there's a difference in the three means, because when we do the omnibus test we do not reject, we have no reason to go on. If, on the other hand, we find out that we can reject this, and some of those means are different from one another, we just don't know which ones or how, then we can go on and build our confidence intervals. So with post hoc comparisons, we make comparisons when differences are evident. That is, when we have detected a difference when we're using the more powerful omnibus tests. So we're really taking advantage of both worlds here. We're getting the more power with the omnibus test, but then if that indeed plays out, that there is a difference, then we can go on and construct these confidence intervals for each of the individual differences. By contrast, specific plan comparisons are when we go ahead and say ahead of time, this is what I'm most interested in, are these specific planned comparisons, and so I'm going to skip the omnibus hypothesis. We may, for instance, say these three comparisons among each of the different pairs of means is what I'm interested in, so let me just go ahead and do those right now and skip the omnibus. Well, you may say, is there an advantage to doing that? The answer is yes, there is. The advantage is your confidence intervals are going to be narrower if they're planned confidence intervals. Well, why wouldn't we just go ahead and do that all the time? Well, remember, there's a payoff. Because even though those confidence intervals are narrower than if you do post hoc confidence intervals, the omnibus test is actually the most powerful way to detect any differences. So you really have this balancing act. You have to decide, what do I want to do? Do I want to have as much power as possible to be able to say there are some differences, knowing, however, that if I do that, my confidence intervals for those specific differences are going to be wider? Or do I just want to go ahead and skip the omnibus and go right to planned comparisons, recognizing that I'm not taking advantage of the power of the omnibus, however, I am making narrower confidence intervals. So there's the catch-22, and you've got to decide which you'd want to do. In most cases, for me, I will go with the planned method simply because I'm going to go right to my research question of interest. Now, if indeed my research question of interest regarding, for example, worldviews and plane risk, and that's a rather exploratory analysis for me. I have no idea how that might turn out and whether there are differences in worldview. If in fact I'm doing that kind of analysis, maybe I want to start with the omnibus. But if I was working in my own area of expertise, I would probably have some theoretical foundations behind my research. And I would anticipate, for example, that one worldview is going to turn out to be higher than the other in terms of perception of plane risk. And then I might want to go to planned comparisons and get as narrow a confidence interval as I can for that situation. Okay, so we're off to a start with looking at how we answer specific questions of interest when we have more than two means. We know that we're going to have some method of error control. We know that we have choices between doing the omnibus followed by post hoc, or we can do planned comparisons. So we've got to get into the weeds a little bit and get more specific about these, which I will do in the next videos.